Swayam Prabha. Digital India. Educated India.
And finally, just to round off the slide, I'll also put in the analog of De Morgan's law here, and for both negating a universally quantified expression and negating an existentially quantified expression. And one final little thing, you might sometimes come across this shorthand. So instead of saying not there exists xpx, there is a symbol of not x's, right? So this says there does not exist an x such that px. Okay, the same thing as this, is just a shorthand. All right, so I'll stop with that. Okay, so this is just a fun little video and a way to look at some of the things we already discussed regarding propositional calculus and predicate calculus. This titled Through the Looking Glass, and you'll see why. So let me tell you what this looking glass is. So imagine a mirror, which you can take a proposition and hold it up against this mirror, and the reflection would show the negation of this proposition. Okay, so I could take the proposition flies Alice, which happens to be false, and its negation, not flies Alice, shows up as a reflection on the other side of the mirror. So, because of that, the truth value changes. So on the left, it was, a false proposition. The reflection is a true proposition in this case. Okay. And conversely, if I hold up a true proposition, it's, a reflection would be a false proposition. So here is another proposition, a true proposition. It says flies Alice or flies Jabberwock. And Jabberwock does fly, so this is a true statement. And what should its negation look like? So if you look at each component in this expression, there are a couple of propositions there, right? Flies Alice and flies Jabberwock. So they will get reflected as their negations on the other side of the mirror. So you'll have not flies Alice and not flies Jabberwock. And they need to be combined somehow. On the left, they were combined using the OR operator. And our goal is that they should be combined in such a way that the whole thing is false. Okay, because the whole expression on the left, it's true. So on the right, it should be false. Okay, so can we do that? Sure, we can do that. We just need to find the right operator such that, you took propositions combined using OR on the left. When reflected, the negations combined using this new operator should show up as, should have the opposite truth value. So you take the truth table of OR, okay? So you look at, say, a cell like, say this, right? Or let's say in this case, this. So flies Alice was false and flies Jabberwock was true. So that's why this was true. We want to make sure that on the other side, if I took the negations of these things, so the same cell here, well, instead of flies Alice, we'll have not flies Alice. So that'll be a true entry. And instead of flies Jabberwock, we have not flies Jabberwock. So that'll be false. And when this true and false are combined using this operator, what you want is just the opposite of whatever is here. So you want false. Okay. So this is the truth table we are looking for. Now, what is this truth table? It's, the order is slightly different. Instead of true, false, I have false, true. But you can just look at it and see, okay, it should evaluate to false on all input combinations, except if both inputs are true, it should evaluate to true. And what is that operator? Well, that has a name. It's the AND operator. So what we have on the right, if we just define the reflection of the OR operator to be the AND operator, this mirror would reflect not just every proposition, that makes up the expression. It will also reflect the operator in such a way that the resulting value would be, reflected to its negation. Okay, and we looked at a particular entry here and made sure it's the opposite, but every entry here was constructed like that, right? So you have, TTTF, so we have FFFT here. Okay, we negated, note that we negated the inputs also. That's because this inputs to the operator are going to get negated in the other side of the mirror. Okay, so what we can do the same thing with the AND operator. We can start with the AND operator and reflect it, and what we want is this operator which, all the trues and falses are swapped, and this operator corresponds to OR because it's false only when both inputs are false, and otherwise it's true. Okay, so basically this means that in our mirror we need OR and AND to be reflected as each other, and it's convenient. Instead of writing formulas, you might also visualize circuits sitting on either side of the mirror. So if I take a circuit with, now it's just a single AND gate, and the two wires are labeled P and Q, then the output wire is P and Q. And in the reflection, what you'll see is that the input wires are now will have values not P and not Q. The output wire will be not P or not Q. That's because my gate got reflected from AND to OR. And we already saw that if you, reflect AND gate to OR gate, this value here will be the negation of this value. That followed from the truth tables of AND and OR. But we have already seen this. This is De Morgan's law, which says P and Q, its negation is the same as what you're seeing here. So that is not P or not Q. Okay, so that's De Morgan's law for negating negating a conjunction. We also have De Morgan's law for negating a disjunction, and that is, in terms of the mirror, this is what it looks like, right? The OR gate is reflected as the AND gate. And you don't need to stop with a single gate. You can have an entire circuit on the left, and every gate is going to get reflected. So the OR gate and AND gates got reflected. The unary NOT gate is going to be reflected just as a NOT gate. You can convince yourself the gate doesn't change. And if you do this much, and if you change the input wires to the negations, then it's not just that the output wire will be the negation of this. Every wire you see here, it will have a value that is the opposite of the value here. Okay, but in particular, the output value, F prime, what I just called it F prime. F prime is this formula or circuit here, and F is the circuit here. So F prime of not P and not Q will be the negation of F applied to PQ. So that's the summary of what we said so far. You can also have quantifiers thrown in here. So if I took a proposition of the form for all x predicate x, so pred is some predicate, so for all x pred x, its negation that you would see on the other side would be that for all is getting reflected as their x's, and pred x will get reflected to the not pred x. So it's another predicate, right? The truth table obtained by reflecting the truth table of pred through this mirror. So just the same way AND and OR got reflected to each other. For all and their x's will get reflected to each other. And you could think of the finite domain case, in which case there is no distinction between the for all and doing a bunch of AND operations. Okay, and their x's is the same as doing a bunch of OR operations. Okay, so let me do this example that we discussed earlier in terms of the mirror here. So this is a quantified expression using two quantifiers. For all x, their xy likes xy. It says everyone likes someone. Right? Their xy likes xy is like someone. Yeah, so for all x likes someone, x likes someone. And we have seen that this is a true statement, because indeed for all x, this predicate, their xy likes xy, evaluates to true, right? Because there is at least one true entry in each of these sets of 3 rows. So it is a true proposition. What does its reflection look like? So for all will get reflected to their x's, and it will get reflected to their x's negation of whatever is here, right? So the negation of their xy likes xy, which you can simplify again by applying the same reflection, same kind of reflection. So their xy likes xy, when you invert it, it becomes for all y does not like or not likes xy, right? In English, that says there is someone, their x is x, such that for every y, x doesn't like y, right? So this x doesn't like anyone. So there is someone who doesn't like anyone. So their x is x who doesn't like anyone, right? So doesn't like anyone is the predicate. And this is false. This better be false, because this a reflection of the statement on the left. And indeed, there is nobody who doesn't like anyone, for the same reason that everybody likes someone. So say everybody likes themselves, right? Here's one more example with the order of quantifiers swapped. So their x is y such that for all x likes xy. So I've rewritten this by combining, for each y I have written all possible values of x, because that's the order of quantifiers here. So their x is y such that this is now a predicate applied for each value of y, right? So and it says for all x likes xy. So every x likes this y. So everyone likes y. So there is somebody who is liked by everyone. That's what the statement says. We can check if it is true or false by just building the truth table. So for so the predicate I'm looking at is for all x likes xy, right? This one, for all x likes xy, meaning, so y is my, I'm applying the predicate to each y, right? So this is saying everyone likes this y. And, it's not the case that everyone likes Alice, so this is false. And in fact, it's false for Jabberwock and Flamingo too. So the claim that there is some y such that everyone likes y is false. And if you look at its reflection, so it's a negation of this. So the negation of this would be for all y, the negation of this. So for all y, what is the negation of this? Their x is x, not likes xy, right? So for all y, their x is x, not likes xy. That is the negation of this entire statement. And in English, that means for everyone, every y, there is some x who doesn't like y, right? So it's not the case that X likes Y. So for everyone, there is somebody who dislikes them. So everyone is disliked by someone. And that happens to be true. So, if you build a truth table for that predicate, it'll be just the opposite of this. Okay, so, I think it's just a fun way to look at negation and De Morgan's law. And if you were curious about all the symmetries you're seeing, this is where it's coming from. The for all, sorry, the and or operators are very symmetric to each other. In the two worlds, they play each other's roles. In the world in front of the mirror and behind the mirror, and the same with for all and their x's. So it shouldn't be surprising that you would see not just and distributing over or, you'll also see or distributing over and, right? Because they are symmetric in the two worlds. All right, so that's it for now.